Hello, class. This week we will be doing talking about sets, which are collections of things that we call elements. Fill in your guided notes as you listen to this lecture, pretty much writing on your notes effectively what I write here as I work our way through these problems. Let's begin with this. Number 1, a set is a collection of elements. For example, consider the set of all cities in the United States. Now, it's pretty common to use capital letters to represent sets. And so this capital A will represent the set of all cities. And normally you put the elements of a set inside a set of curly brackets like this, which takes a little bit of practice to learn how to do by hand. And so start naming some U.S. cities. Boston, right? Los Angeles or L.A., San Francisco, Phoenix. Obviously, we're not going to spend the time doing all of this. There's way too many cities. So ... then end the parenthesis, or end the curly brackets. Or you can just simply say something like A is equal to the set of just all U.S. cities. Now, each city that's in the United States is considered to be one element of this set. And if you were to write down an element, let's go with Boston. A symbol used in mathematics to indicate that Boston is an element of the set of all cities is you do this little, it looks like a C with a line in the middle of it. And then you can put the capital letter A to represent the set of all cities. This is a mathematical sentence, essentially, that says Boston is an element of the set A, where A is the set of all U.S. cities. It's just a mathematical way of saying that Boston is a U.S. city. It's an example of a U.S. city. And then if you were to take a city that's not in the United States, let's go with Berlin. Berlin being the capital of Germany, you would say something like, put a slash through this symbol here, and this one reads, Berlin is not an element of the set A. In other words, Berlin is not an example of a U.S. city. Okay, the next item to discuss here, if all the elements of a set A can be found in a set B, then we say that A is a subset of B, or that B is a superset of A. Okay, let's do an example here. Let's go with the exact same set A, all U.S. cities, and let's say set B, capital B, is all Arizona cities. Right, so you have Phoenix would be an example of something that's in the set B, but Boston, in Massachusetts that is, maybe there's a Boston, Arizona somewhere, but I don't know of one, but referring to Boston that's in Massachusetts, you would say is not in the set B. However, everything that's in the set B is also in the set A, because all Arizona cities are also U.S. cities. And so a symbol that we would use here to represent this relationship is to say that the set B is contained, or a subset, it's kind of like is an element of symbol that's right there, but without the line in the middle. And sometimes it looks kind of like a really long, elongated symbol like this, the one I'm making right now anyway. But you can just draw something that looks like a C. And then we put this symbol here, the set A here. Now, this is communicating that anything that's in set B is also in set A, but not true the other way around. Right? There are some elements of set A that would not be in set B. For example, Boston is here in set A, but Boston is not in set B. There's another symbol that can be used here. You can also say B subset and put a little line underneath that and then put A. This is communicating two possible realities, that B is a subset of A, or potentially that B is the same set as A. Now, in this particular case, where B stands for, or B is the set of all Arizona cities, and A is the set of all US cities, we know for sure that B is not the same set as A. So the more informative symbol would be this one right here. But that doesn't mean that this symbol isn't true still. It's kind of like with inequalities. For example, if I were to say something like 2 is strictly less than 5, I think we would all agree with this. But it's technically true to also say this. 2 is less than or equal to 5. Now, it's clearly not equal to 5, but putting this partial equal sign on this inequality just allows whatever's on this side of the inequality to be either 5 or less. Whereas, I don't know why that didn't erase, there we go. Whereas this symbol here indicates, it's called a strict inequality. It indicates that the number that's on the left is certainly less than and not equal to the number that's on the right. As far as subsets are concerned, these symbols here have similar meanings. And in fact, in the case here, oops, let me move some of this stuff over a little bit. If in fact B and A are not the same set, but B is, everything that's in B is also in A, then this is the more informative, as we said, the more informative notation, because it tells us that B is not equal to A. But it's still technically correct to write this. Now, if A and B are unknown sets, let's say I didn't tell you that B stood for all Arizona cities, nor did I tell you that A stood for all US cities, and you saw a symbol, an expression that looks like this one, then this would allow for the possibility that the two sets could be equal. So either B is a subset of A but not equal to A, or B is in fact equal to A. Now, this symbol here could be written backwards, just like an inequality, right? If you come back over to these two examples here, I could also put the 5 over here and say 5 is more than 2, or 5 is greater than or equal to 2. So you could switch the order in which you write this, and it communicates the same thing. Same thing is true with the subset symbol. If I put A, which is all US cities, on the left, and B, which is all Phoenix cities, on the right, then you got to make sure that this symbol here is opening towards the superset. It's almost like the B is, I don't know what to say here, but it should open towards the superset. Sometimes when you see it written this way, you can think like B is contained in A, because this kind of looks like a C. Of course, that would go out the window if you tried to make sense of this one, because when you write this symbol backwards, it doesn't look like a C any longer. But anyway, this one here, you could also write A is a superset of B. If you read it this way, that's how the language I would use. A is a superset of B. But if you read it this way, I would say B is a subset of A. In the case where the subset is not equal, like in these cases here, we have this terminology. I think I wrote it here. Yes, if a subset of B, if A is a subset of B, but the two sets are not equal, then A is called a proper subset. Right. So this is referring to this notation. We have a proper subset. This suggests that one set is contained in the other set. All the elements of one set are also in a larger set, but the two sets are not equal when you say that they're proper. And then there's something called an empty set. The empty set is a set that has no elements. And the symbol for the empty set looks like a 0 with a slash through it, and it's equal to a set that has nothing inside it. Sort of an uninteresting set, but you can think of it as a set. It's a set with no elements, called the empty set. Technically, the empty set is a subset of any other set. Like, this is a sort of a trivially true statement. It's sort of like saying 0 is less than or equal to any positive number. Like, you put any positive number over here, even decimals, whatever, 0 is certainly less than or equal to it. You could make that sort of parallel. The empty set is a subset of all sets. Okay, let's move on to number 3. Let's put some of this to the test here, some of these symbols. Let A equal the set of numbers 1, 3, 5, 7, 9, 10, 12. B will be the set 1, 5, 7, 9, 11, and C will be 10, 12. Indicate whether each statement is true or false. Explain your reasoning. Okay, so our first statement here is, this reads literally, 3 is an element of the set A. That's how you just want to translate that mathematical symbol. So we're just asking ourselves, is it true that 3 is one of the elements of A? So you track down A, which is right here. 3 is certainly an element of it, so this would be a true statement. And then you're supposed to explain your reasoning, but you could just say simply it's because 3 is an element of A. You're pretty much just restating what this brief symbol means in the first place. The next one, 10 is an element of B. So we look at B, we look at the elements of B. There's 5 of them. I don't see 10 in there. So we would say that this one here is false. And a similar sentence you could write, because 10 is not an element of B. But a better symbol would be then to say, this would be a true statement, 10 is not an element of B. So that statement's true. This statement here is the false one. Let's see, next one, 12 is an element of C. So we look at C, 12 is certainly in there, so we got another true situation. Again, you could write because 12 is an element of C. All right, so now we're getting to the subset notations. So B is a subset of A. So we go back up here to B, and we have to just determine whether or not all the elements of B are also in A. We'll just do this, one at a time, systematically. Let's focus on the 1. 1 is in B. And, let's see, I don't know what that was. There's 1, okay. And 1 is also in A, check. 5 is in B, 5 is also in A, check. 7 is in B, 7 is also in A, check. 9 is in B, 9 is also in A. Uh-oh, but we have a problem here. 11 is in B, but there is no 11 in A. So this means that we have a false statement. When you have a set that's not a subset of another one, and notice this is using proper subset notation, it's not giving us the possibility with the 2 sets are equal, then you simply just have to rewrite this symbol and put a slash through it, and this would be a true statement. Right? The given statement is false, but put a slash through it, and then it becomes a true statement. Okay, let's look at C is a subset of A. So let's take a look at C. And see, 10 is in C, 10 is also in A, 12 is in C, 12 is also in A. So that means everything that's in C is also in A, therefore C is a subset of A. Additionally, C is a proper subset of A because A has some things here that C does not have. So this symbol is a good symbol. And we would say true. Now technically, we could also write this, and this would be a true statement as well, technically. because this communicates that C is either a proper subset of A or that C is equal to A, and one of those two statements I just said is true, therefore overall the OR statement is true. But this is the preferred way to communicate this because it gives us the extra information that C is a proper subset, which happens to be the case here. So maybe we would say something like, is technically a true statement but this, referring to that statement, is better. Okay, let's get rid of those little arrows. Next one, C is a subset of B. So we go over here to C and we say, okay, what's in C? C has 10, but B does not. So as soon as you find something that C has that B doesn't, then there's no way that C can be a subset of B. So this is a false statement. However, this would be a true statement. That would be false. Okay, let's move on to the next item here in our notes. List all the subsets of the given sets. Identify all the proper subsets. Determine how many subsets of proper subsets. Let me read that again. Determine how many subsets and proper subsets a set of size n has. All right, so the size of a set is just how many elements are in it. So in this first case here, the set A has size 2. And we want to list all sets that are subsets of A. Well, as we said earlier, the empty set is always a subset of any other set, including of itself. Of course, if you write this statement, this is not a good statement because the two sets are equal, so you would need the partial equal notation, if you will. This is a good statement. This is a bad statement, right? You can't have a set be a proper subset of itself. You need them to be equal to have a good statement. So keep that in mind. But here, since A is not the empty set, A has 2 elements, this symbol here without the little partial equal sign is appropriate. Okay, then sometimes you have single or one element sets. So A all by itself is a subset, or little a is a subset of capital A. Little b all by itself is a subset of capital A. And then the set itself is a subset of itself. Now for this last one, you do have to include that little partial equal, because if you didn't put it there, then it'd be communicating a false idea. The 3 proper subsets are these 3. Those are the subsets of A that aren't A itself. You know, these 3 subsets right there. The empty set, the set of A, little a by itself, and the set of little b by itself are all different proper subsets of A. Okay, let's look at a set that has 3 elements. Okay, so again, we have the empty set will be a subset of B. We have all the single element sets, and sometimes with a single element set, you can get away with a couple symbols here technically. Like this little D, for example, I could say is an element of B, because D is one of the elements of the set. Or you could say D is a subset of B. And you just think of this as a one element set. Right? So when you're talking about elements, technically both of these are acceptable expressions. One of them just, this symbol is used specifically for elements, and this symbol is used for elements or sets. And you can think of an element as a one element subset. But let's just go with subset notation. And I'll put the little d in curly brackets. I don't know why I skipped the C. Let's move that down just to go in order, make sure we're systematic. So little c is a subset of B, little d is a subset of B, and little e is a subset of B. Those are all the one element sets. Now let's do all the two element sets. Let's see, C and D together form a set, is an element or a subset of B. C and E together form a subset of B. And D and E form a subset of B, and these are all the two element subsets. And then finally there is a non-proper three element subset, which is actually equal to the set B itself. So you need that partial equal component of our subset notation. And in the end, we count these out. How many different subsets do we have? We have 8. And the proper ones are, those ones are the proper. And just for the sake of consistency, I'll circle those as the proper ones. Oh, and let's count how many are proper. There were 7 proper subsets and 8 total subsets. All right, now let's consider a 4-element set and write down all the different possible subsets. At this point, I should make clear something that may be, needs to be said. If you were to take a list, if I were to take this set B and change the order of the elements, the question is this the same as this ordering? Are these the same sets? And when we're talking about sets, we're going to assume that ordering of the objects does not matter. All that matters is that they're the same collection of objects. So you would consider these the same. It's unlike a sequence of numbers where sequences implies that order matters, but when you talk about a group of things or a set of things, the order is not significant. So this set here is said to be the same as this set here because they both have 3 elements, and those 3 elements are the same. Also, if 2 elements within a set are identical, they don't need to be listed twice. For example, what if your set had 4 numbers in it? This set actually only has 3 different numbers in it, and so we would not bother writing the 2 twice and just say it's really a 3-element set. So we want the elements to all be different in the set as well. Another subtle distinction that needs to be made about sets. Okay, now let's look at a 4-element set. So once again, 0 will be a subset of set C. You can see why the subset notation, when you do this in print, it looks like a really elongated flat C, and it would look more something like this. But when you're writing quickly by hand, it looks like you're just saying CC, right? So that sometimes is a problem. Sometimes people write a smaller little c, so it looks like that. 0 is a subset of C. Or we could want to avoid this issue. We can say, well, let's not call the set C. Let's give it a different, let's call it set capital D, if you want to avoid that issue, right? But anyway, 0, or the empty set, is a subset of D. Let's go ahead and go with D. All the single elements, so F is a subset of D, G is a subset of D, H is a subset of D, and I is a subset of D. I'm not going to bother putting these all in curly brackets. When it's a single element set, then sometimes people don't bother putting the curly brackets around it. Let's do all the 2-element sets. So now we just have to be very careful that we get all possible pairings here. So we could have F and G, and those are the 2 elements. It's a 2-element subset, and it's a subset of D. In fact, I'm going to also stop writing subset of D. Like, that's true for all the things I'm writing, so why bother write it a million times? Let's see, what else? We could do F and H is another possible one, or F and I is another one. And those are all three that have F involved, so let's not use F. Let's go with, we have G, H. We have, I'll go up here just for space sake, we have GI. And it's tempting to put GF as another one, but FG and GF are considered the same, right? Given our other conversation, so that's not a distinct one. And I think that's all. There should be three of them that involve G, and they're all accounted for. This one, and this one. Okay, so let's shift to G and F are not involved. There's only one left, HI. And it should be the case that there's three that involve F, these three. There's three that involve G, these three. There's three that involve H, those three. And there should be three that involve I, right? Those three. And those are all the 2-element subsets. Now let's think about all the 3-element subsets. Well, to have 3 elements out of the 4, we just have to vary which element is not in the subset. So the first one I'm going to do is omit the I. So F, G, H. Now let's omit the H. So we have F, G, I. Now let's omit the G. So we have F, H, I. And now let's omit the F. We have G, H, I. And there's 4 3-element subsets. And then finally, the 4-element subset, F, G, H, I, is also technically a subset. But if you were to use subset notation, you would need that partial equal sign on this one. All the other ones you can get away with a proper subset notation. Well, how many was this? Let's count these up. Let's see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. All right, seeing 16 there. So you have 16 subsets, of which all but one of them, 15, were proper. Okay, have we done enough now to determine a generalized rule for how many subsets a set of size n is going to have? Let's see, there were 4 total in this case, 8 total in this case, right? 4 total, 8 total, then 16 total in this case. You see a pattern? Looks like we are just doubling every time we get another element. So I'm guessing a 5-element subset is going to have 32 subsets. And the general rule is, let me make that a little bit smaller, make some space here. If A has n elements, then there are, have you figured out the pattern? Here we had 2 elements and we had 4 total subsets. Well, that's the same as 2 squared. Here we had 3 elements, and that was 8. That's the same thing as 2 cubed. Here we had 16, and that's the same thing as 2 to the 4th. And that was coming from a 4-element set. So it looks like that 2 to the n will be the number of subsets if the set has n elements to begin with. And the reason that is, if you have taken a class that involves counting possible outcomes, let's look at the 4 different elements. When you're making a subset, each element has 2 options. It's either in the subset or it's not. So there's 2 options for whether F is there or not. There's 2 two options for G, there's two options for H, and there's two options for I. So we have 2 times 2 times 2 times 2, right? 2 to the fourth. You're going to be 16 total possible outcomes because each element was a sort of binary possibilities. It was either there or it wasn't. And use the multiplication principle to multiply those possibilities with each other. It's kind of like saying you have 3 different pants and 4 different shirts, and you ask yourself how many different clothing combinations could you wear. Well, since each choice has so many options, you would multiply and say there's 12 different outfits, right? Because you could do the first pair of pants with any of the 4 shirts, or the second pair of pants with any of the 4 shirts, or the third pair of pants with any of the 4 shirts, and you create 12 different possibilities. This is the multiplication principle when it comes to making a decision that has multiple options, multiple smaller points of decision. So will F be in the subset? Yes or no? 2 options. Will G be in the subset? Yes or no? 2 options. Will H be in the subset? Yes or no? 2 options. Will I be in the subset? Yes or no? 2 options. Multiply those together. We have 16 total possible outcomes here. So 16 subsets. Okay, let's go on to the next one. A Venn diagram. You've probably heard of this term before, but let's review this. A Venn diagram is a representative image that uses closed regions to represent sets. Each set can be imagined. Okay, let's just do that first sentence. Let's go back to that set A that represented all U.S. cities. So you can do a circle or a blob or something and put an A next to this, or I like to put the A on the boundary like this. So this is the set A, and it's a closed region. Usually people use circles and overlapping circles and whatever for Venn diagrams, but the shape doesn't matter as long as it's closed. And it's a visual tool. If you put something inside of A, like a little dot, and that represents an element of A, and maybe that represents Boston. Right. And another dot represents, Phoenix. And then all the different U.S. cities would be represented by some element inside the set. Pretty much any dot you put inside here is going to be an element of that set. So inside the closed region means in the set. Whereas if you put, Berlin would be out here. It would not be in the set of U.S. cities. That's Berlin being the capital of Germany. Or even things that aren't cities, like you could put a dot that says, I don't know, a tree. A tree is not a U.S. city, so you'd put a tree outside the set A as well. Let's see. Each set. So this is true for just all sets in general. Any set that you can imagine can be also imagined to be a subset of some superset called the universe set. So you can situate, say, set A, for example, in something that you're going to say is the universe. We only want to think within the context of a larger set. So, for example, I might do a Venn diagram that includes A, that I'm going to call set B, and let's say set B represents all world cities. Notice I drew B in such a way that tree was still outside of B even. So tree is outside the universe set. And for universe set, sometimes we use a capital U just to indicate that, let's call that capital U for universe set. Universe sets are good because they allow you to focus on just only certain kinds of things to begin with. So you tune out all the stuff that doesn't even seem relevant to the question at hand, like trees or other things. If you want to think only about cities, and then you want to, within that context, then also think about U.S. cities, then you would call the universe set would be all world cities, and then the set A would be a proper subset of that, in this case, would be all U.S. cities. But you can imagine even a new universe. You could say, you can make the universe bigger and say that, let's call this universe 2. That universe 2 stands for all cities in the galaxy. So maybe there's some other planets out there that also have cities that we don't know about, and so you have a bigger universe. So you could have also said the universe was not world cities, but something smaller. Maybe get rid of the word world here and say that the universe set was all Northern Hemisphere cities or North American cities or something like that to suggest that we're looking within a context that's more than just U.S. cities, but you want to define how much more exactly. And things that are outside the universe sets, typically we just don't even worry about thinking about. It's just, for whatever reason, they're just not relevant to our analysis. So goodbye, tree. I love you, tree, but goodbye. All right, create a Venn diagram to show the relationship among the sets described below. Identify which sets are subsets of another set. Describe the complement of each non-universe set. Ooh, I forgot to mention we forgot to talk about complement. The complement of a set A is the set of all elements that are in the universe set but not in set A. So when it comes to the notation that we're going to use, let me actually move a few things around here to give myself a little more space to write. I'm going to move that over here, move this over here, and let's bring this over there as well. There's several symbols that are acceptable for indicating the complement of a set. One is to put a bar, and this would be all. So a bar, this is why you need to establish a universe set so that you can say that what a bar actually is. Since our universe set is world cities, a bar is going to be all cities that are in the world but that are not U.S. cities. So all non-U.S. world cities. Maybe there's probably a longer, better way to say that so it's clear, but just all cities that are in the world but not in the U.S. That's defined. That's called the complement of A. And another symbol for complement is to put a little prime after it. Or another acceptable one I've seen is put an A with a little C exponent to stand for complement. So just be prepared depending on where you look. If you look online on YouTube, and you might see different symbols that all represent the complement of a set. If you're going to do some shading, and you wanted to say, hey, where in this Venn diagram is a bar, and we'll do some shading for it. In fact, let's do some color coding in general. The set A is going to be green, and its complement is going to be red. And let's do some shading here. So anything that's the set A, we're going to shade green. Oops, there we go, the highlighter. Oops, wrong color. Okay, and anything that's in the universe but not in A is said to be in the complement. And so this ring, this outer ring that's still within U, but it's not in A, is the complement. Okay, forgive the sloppiness, but you get the idea. Sometimes when you have a universe set, maybe you want to do it this way. You would say, all right, so here's the universe set. That's all world cities. And you can just sort of break it into two distinct pieces by just putting a line down through it somewhere and saying, oops, I don't know what just happened there. Here we go. That, one side of this is the complement of A, and the other side is A. Right, so this is one approach. Here's A, set A, and here would be, A complement. And together they make the universe set. So there's a variety of ways you could do the Venn diagram to break a universe up into some subset A and its complement. Okay, now back to this question 6. Identify which sets are subsets of another set and also describe the complement of each non-universal set. Okay, so we have plenty of space here, so we're just going to make a nice big universe. So that ring represents the universe set, and it is the set of all people. And we might want to be clear, like all people who ever lived, or what? Let's just say all current people, all living people is the set U. So you might put like Ben Franklin over outside this set because he's not living, but you would put inside here because you are living. Okay, so U is the set of all people, or if you want, you could say U is the set of all people who are or have lived. You decide, but let's go with just all living people. A is the set of all females. Well, every female is a person, and so A is going to be a subset of U, but not every person is a female, right? So A is definitely a proper subset. So you're going to, and somewhere in here, we want to put a enclosed area that stands for all females. B is the set of all parents. So if you are a living person and you have, we'll say, a living child, then you are currently a parent. Or maybe even if you had a child that's no longer living, we can maybe still call you a parent, even though your child maybe has passed before you. But whatever, those are just, we're quibbling over details here. Let's just say if you've ever had a child, then you're considered a parent as well. Well, certainly every parent is also a person, and let's assume we're talking about human parents, right? Not like parents of a cat, for example. Let's just go with human parents. And same thing with the females, right? We want to specify, maybe here we could say that all human females, because a female cat would be outside our universe if our universe is just humans. So B is a set of all human parents. Well, not every female is a parent. And so there's going to be some set B that we now want to situate, right? How is this? Certainly it's going to be inside U. So this would not be a good spot. Out here is not a good spot. It's going to be inside here, but there's going to be a little bit of overlap. There's going to have to be some overlap with the set A, because there are some people who are both female and a parent. But then there are also females who aren't parents, and there are also parents who aren't female. And then set C is a set of all female doctors. So now we have some set C, and the question again is, how does this situate, or what relationship does this have with all these other boxes? All right, so we've got definitely, it's going to be inside the universe entirely, so it has to be somewhere inside the universe. And the question is, are there female, let's see, the set of all female doctors. So in order to be a female doctor, you have to be female. So that's going to push C into A as well. Like, we can't have, this can't be the case, because if you left it there, that would suggest that you would have the existence of someone who's not a female, yet they are a female doctor, which doesn't make sense, right? So we definitely need this set to be entirely in A. But how does it interact with B? Does it overlap B? Do they not overlap? The question will be, is it possible to have a female doctor who's also a parent? And the answer to that is obviously yes. So let me redo some of these labelings now that I kind of get a sense for how I want this to be oriented. So we're going to put all the females, and you can make a circle for females, or you could do this. Just split the universe into males and females, right? Males here, females here. You have a few options on how to do this. If you do use a circle to stand for all the females, then where would all the males be? You would say, well, these would be all the males. Would be some other circle. There'd be no overlap, unless you want to account for, some people who might be considered both male and female. But let's just think more simply. We'll say either you choose to be male or choose to be female, but you don't choose both. Let's just say that for simplicity's sake, even though that may not be the case. But if you leave the two circles like this inside the universe, it sort of implies that there's things here that aren't considered male or female. And again, you might make the argument that there are some people who are asexual, and certainly that's true that they are out there. But so maybe that is not as simple as just saying if you're a human, you have to be a male or a female. So maybe we do need to keep our circles distinct, or not fully inclusive of all humans. Anyway, I don't mean this to become a political or moral discussion. This is an example of how to work with sets here. Okay, so let's go back to here. Here's the set A stands for all females. Let me push that over here. The set of all parents we decided would be overlapping the set of females, but still in the universe set. And then the set of all female doctors was going to be some sort of set like this that was contained within the set A, but also potentially overlapping the set B. Okay, then it says identify. I'm going to give myself a little more space by I'm now going to shrink this down. There we go, put that there. Identify which sets are subsets of another set. Okay, well, by definition, all of these are subsets of our universe. Right? So you would say A is a proper subset of the universe, B is a proper subset of the universe, C is a proper subset of the universe. Any other relationships? Could we say this? A is a subset of B. Well, not everything that's in A is also in B, so this would be not a good statement, so we don't want this one in our list of all the subset relationships that are out here. Similarly, B is not a subset of A, but C is a subset of A, right? Because every female doctor has to also be a female. And I think this is all of our subset relationships that are possible here, given our particular drawing. All right, so we've done, now let's do this. Describe the complement of each non-universal set. And by describe, let's use some words. So if I were to say, we don't want to bother with the complement of the universe, that would just be all non-people or all dead people or whatever. Let's just do the complements of the non-universal sets. So what is a complement? This would be all human non-females. So definitely all males, and maybe any other special class that you might want to put in there, but definitely all males. Unless you think there's a class where there are some people who are both male and female, but again, let's not to marginalize anybody, but let's just, for simplicity's sake, let's say that doesn't happen for this particular example, even though it does happen in reality. The complement of B, and let's use various notations. Let's put the bar above B. The complement of B, it would be all non-parents, all human. So I put the word human in there so that to indicate that we're still in the universe. Because if I just say all non-parents, then you might say, well, a brick. But no, we want to be within our universe, and a brick is not in our universe. And then the complement of C, let's do C with a little prime sign by it. The complement of C would be all human, non-female doctors. So a female lawyer would be in this set, as long as that lawyer wasn't also a doctor, right? If you want to do like shading, like you say, hey, shade in set A, and so you would just, shade in all of set A, including set C, right? Because everything that's in C is also in A. I would say, okay, there's my set A. Where's set C? You would just shade in set C. Where's set B? You would shade in all of set B. If I said, hey, where's a complement? You would shade in everything that's not in A. So just get to shade everything that's still in the universe, right? So you got to constrict yourself to the universe, but you would not draw anything in A, right? So it looks something like that. That's a complement. etc. Right? B complement would be everything outside B, but still in the universe. You get a shade in everything in the universe, just don't shade in anything in B. That would be B complement, etc. Okay, number 7. Let's talk about the union of two sets, A and B. The union of two sets is the set of all elements that are either in A or in B. Okay, so let's talk about unions. Let's use numbers for this case. All right, so A is a set of 1, 2, 3, and B is a set of 2, 4. The symbol for doing a union is to put a U without a tail. Don't put a tail on the U, so a tailless U, and then putting a B after it. This stands for the union of A and B. And it means take everything that's in A or in B and make one set out of it. So you could just begin by writing down everything that's in A, followed by writing down everything that's in B, and then eliminate anything that got repeated twice. Like I don't need to have that 2 in there twice. So in the end, the union is 1, 2, 3, and 4. These are all of the elements that are either in A or in B. And some of them might be in both, like the number 2 is in both. The intersection of two sets A and B is the set of all elements that are in both A and B. So when I say, hey, do an intersection, you do an upside down U with no tail. So this is the intersection notation, A intersect B. And it's everything that's in both, and only the stuff that's in both. It has to be in both. So the only element that is in both is 2. Two sets are disjoint if they have no elements in common. Well, A and B do have an element in common, so let's invent a new set C. Let's say C has 4 and 5 in it. Notice set A and set C have no elements in common. If you try to do an intersection of two sets that have nothing in common, then you would get the empty set back. Sometimes people put the empty set in brackets, by the way, but you don't have to do that. And when you see this symbol right, or see this statement right here, A intersect C equals the empty set, this is just a mathematical way of saying that the sets A and C are disjoint, meaning they just don't have any common elements. So we would say A and C are disjoint. Okay, let's look at 8 here. Use a Venn diagram to depict all the ways two sets A and B can relate to one another. In each case, identify their union and intersection. Okay, so we have a set A and we have a set B. And we want to think all the different ways that they can, interact with each other. So one possibility is that they're disjoint. They have nothing in common. Another possibility is that they do have some stuff in common, but not everything. Like B has some of its own elements and A has some of its own elements, but then there are some elements that they both have. All these pictures where B is partly overlapping A represent that idea. Or you have this possibility, right, where make A a little bit larger, where B is actually contained entirely in A. Right, so here's another possibility. Or you have the possibility that they're like the same set, right? I didn't draw this so they're the exact same, but imagine they're the exact same set. And that's another possible way that these two sets can relate to each other. So let's use Venn diagram to represent these possibilities. So the first Venn diagram I'm going to do is let's do where they're disjoint first. Okay, so there's one possible. We'll call this case 1. Case 2. All right, let me copy this, paste, is that there's some overlap. Case 3 would be something like where you have set A, but set B or one of the sets anyway, is entirely in the other. And since we're arbitrarily naming A and B, you could say that this is the same case as saying that B is the superset and A is the subset. Right? Just the idea that one set is a subset of the other, a proper subset of the other. So let's just go ahead and just say that without losing generality, that A is the superset and B is the subset. And then case 4 is if they're the exact same set. So this is A and B both. Let's do this to indicate that A/B, they're the same set. In which case by the way, when two sets are technically equal, then this statement is true, and so is the reverse. And this concludes that they're the same set. If A is a subset of B and B is a subset of A, and you need the partial equal signs on them, of course, in both cases, then it must be true that they're the same set. Okay, and then in each case, identify their union and intersection. Okay, so let's say that I'm going to do some color shading to help coordinate this stuff. And I also want to do some copying. Let me go ahead and get rid of the cases here just for space's sake, although feel free to keep them in your own work. Let's put that a little bit closer. Okay, so these are the 4 cases. Now let's do some shading for the union and some shading for the intersection. I think I'm going to have to make these a little bit smaller in each case, just to make space for all this. All right, so these are the cases. There's 4 cases. Maybe this will be helpful. And then let's do some shading for their union, and then some shading for their intersection. And the union's going to be, we'll use red shading for the union, and let's do green shading for the intersection. I might have to go with a smaller tip marker here. Okay, so when 2 sets are disjoint, like they are in case 1, then their union is really just a combination of everything that's in one or the other. So you get it to shade something like this. When 2 sets overlap a little bit and you do the union, then the union just winds up being anything that's in A or in B. So you get to just shade this sort of common blob here and say that's their union. That's exactly what happened, by the way, in our example up here with A and B, right? A and B had some common elements, but they also had some distinct elements, and when you did their union, you wound up with just a collection of all the elements, both the ones that were common and the ones that were distinct to the different sets. When you have a subset situation and you do a union, then you wind up just getting the superset, because everything that's in B is already in A. So when I say, hey, what's the union of A and B, you wind up just getting A again. By the way, in symbols, it would say something like, in a case like this, the union of A and B is just going to wind up being A all over again. Right? That's not the case for the first 2 cases. And in the case where the 2 sets are the same and you do a union, of course, you just get everything that's in those sets anyway. Right? So in a case like this, which kind of a trivial case, if you do A union B, you get the set A, but you also get the set B because A and B were the same to begin with. Okay, the intersections. In the case where two sets are disjoint and you do an intersection, there is nothing in common. So there's nothing to shade, right? The empty set is the intersection. Right? And in this case here, let's write this formally. Go away, thank you. We would say the intersection of A and B is the empty set. They're disjoint. However, when they overlap a little bit and you do the intersection, you get just what's in common. Right? Because you would consider whatever's in A, and then consider, as a second consideration, anything that's in B, and only the stuff that got considered twice. You see that's shaded a little bit darker. That's going to be in the intersection. In other words, just keep what's in the overlap. There's their intersection. In the case where you have a superset subset situation, proper subset situation, the intersection is everything that's in both. Well, since B is a proper subset of A, everything that's in both is just B all over again. So in a case like this, A intersect B will be equal to the subset, whereas over here, they equal the superset. And I'm going to be picky here and make this be consistent with my color coding. It's just the way I am. And when we have A and B are the same and you do an intersection, then you get everything's in common because they're the same sets. And so in this case here, A intersect B is just equal to A again, which is also just equal to B again. They're the same set. All right, so this is all the different ways in which two different sets, or potentially the same set, two sets, can interact with each other, and then how to think about the union or the intersection in each of those cases. Number 9. Suppose the universe set is a set of all counting numbers up to 10. Create a Venn diagram to show the relationship among the sets described below. Then for each set that follows, identify its elements and shade in the appropriate portion of that Venn diagram. Okay, so our universe set. Let's do a small picture I can repeat. I'm going to wind up copying this. There's a universe set. So this just contains the numbers 1 through 10. A is clearly a proper subset of that. So we can put set A as a proper subset. B has some elements in common with A, but some distinct ones as well. So then I'm actually going to redo A so it's a little bit bigger. B has some elements that are in A, but some of its own elements. So there's going to be how B interacts with this. And then C has only elements that are in A, but none of them are in B, right? So this 9, 10, there's no 9, 10 in B, but both of them are in A. So this means that C would be a subset of A. So you would have a subset inside here, we call that C. Actually, let me make this a little bit bigger. So I'm going to put some numbers, I'm going to put all the numbers in here. Okay, so where's 1? 1 is in A, and it's also in B. So it gets, whoops, I don't know, my hand just pushed something I didn't mean to. Here we go. 1 is in A and in B both. So 1 would be located in this portion of our Venn diagram. We're going to go 1 through 10. Where's 2? 2 is in B, but it's not in A. So 2 would be in this portion of the Venn diagram. Where's 3? 3 is in none of it. So 3 is in the universe, but it's in none of the other sets. So it's outside that blob of sets, but still in the universe. 4, similarly, right? 4 is also in the universe, but not in any of the other sets. 5 is in B, but not in any of the other sets. So you put 5 over here. 6, it's in the universe, but not in any other set. 7 is in A and B both, so 7 belongs here again. 8, I don't see in any of the sets, so 8's going to be in the universe, but not in any of the other sets. 9 and 10 are both in C, and they're also technically in A. So there we go. There's 1 through 10, and then 0. Right? 0 would be outside. 10 would be outside. Negative numbers, when we get there, will be outside. Fractions, when we talk about those, will be outside, right? Because those aren't counting numbers. Fractions aren't. The counting numbers are 1, 2, 3, 4, etc., up to 10. So there's lots of numbers that are not in the universe. And then other things like a pig would not be in the universe because a pig is not a number, right? A tree, a brick, etc. Okay, so now let's do A intersect B, identify what's in the intersection, and then do shading. So for the shading purposes, I'm going to copy this, put that here, and let me get rid of hide all the numbers that aren't relevant. I'll just get rid of all the numbers. A intersect B. The intersection of A and B is where they overlap. So it's just this portion of our Venn diagram. And what elements are those? Well, those are the elements 1 and 7. These are the elements in the intersection of A and B. A union B. Right, so let me copy this again. In fact, how many of these do I have to do? Several. Well, let me do this. Delete that. Let me erase that shading and copy unshaded. Okay, so we have to do some shading for each of these portions here. And let me shrink the size of this just slightly. Okay, so there's our 5 shadings we're going to have to do. All right, A intersect or A union B. This is anything that's in A or in B. So shading wise, it's going to be anything in A or in B. So anything that's in A, which includes C, or in B. So we get to shade all this stuff. And there's our union of A and B. So what are the elements that are in the union? Well, you can just look at A and B and just write down every number that you see there. And the ones that repeat only write once. Right, so there's a 1 in either of those sets, there's a 2 involved, there's no 3, no 4, there's a 5, there's no 6, there's a pair of 7s, we'll just write it once, no 8, but then a 9 and a 10. Right, these are the 6 numbers that are in the union of A and B. Well, now we're getting something interesting. A intersect, or A union C complement. Okay, this is interesting. A union C complement. C complement is everything that's outside of C. Let me do some shading here in red. Anything outside of C but still in the universe is part of C complement. And we want to do a union of that with everything that's in A. Well, A, I'll do that in green, is right there. So anything that got shaded, and not even doubly shaded, just shaded, is in the union. In other words, the union is going to be, it winds up being the universe, because everything ultimately got shaded at some point. So we get to just do the universe, shade all the universe in. Another way to do this is to come up here and say, hey, what's C complement? C complement is everything that's in the universe but not in C. So it's going to be 1, 2, 3, 4, 5, 6, 7, and 8. Right? Everything that's not in C but still in the universe. And then we just did a union of this set with A. Right? So I'm looking at a union with A complement. And every number is accounted for because the 9, 10 came along with A. Right? They were the numbers that finally got shaded in when I also shaded in A. I got the 9, 10 added to the list. So in this case, oops, I did not want to erase this part. In this case here, A union C complement just winds up being the universe set, right? Which is 1, 2, everything up to 10, the whole universe. Okay, next one we have B union C, and then a complement after the fact. Okay, so B union C, and then a complement. So looking at this, anything that's in B is going to be in B union C. Anything in C is going to be in B union C. So there's B union C. But now I want to do the complement of that set. So in other words, we now have to shade everything that's in the universe that's not currently shaded. All right, so that's going to really wind up shading. We flip our shading relative to the universe. Everything that's outside C and also outside B we need to keep. Oops, darn it, I made a mistake. All right, thank you for being patient while we got through that. So this would be the complement of B union C. You know, if you find it helpful, you can come up here and say, hey, well, what is B union C to begin with? Oops, no tail on that U. B union C. Anything that's in B or C. So it's going to be 1, 2, 5, 7, 9, 10. Okay, that's B union C. And we want to now do the complement of this with respect to the universe. So everything that's not in this union. So that's going to be 3, 4, 6, and 8. Three, 4, 6, and 8. Right, that corresponds to those numbers that we see up here. The only numbers that are not in B or C, 3, 4, 6, and 8. Now we have A complement intersect C. All right, so let's do A complement. Shading wise, A complement is everything that's not in A but still in the universe. There, I've shaded it. And we want to intersect that with C. Well, C is right here. And the two things that I just shaded, what elements do they have in common? Well, they don't have anything in common. I didn't do any shading twice. So in this case here, we just get the empty set. All right, because A complement, the things that are in A complement, so looking at A would be, things not in A would be 2, 3, 4, 5, 6, and 8. So now if I do A complement intersect with C, what did they have in common? Well, they don't have anything in common, right? We have the empty set. So nothing to shade in that case. And let's do our last. Do some problem solving with Venn diagrams as a tool to help us. Create a Venn diagram to organize the following information and answer the questions that follow. 100 students were interviewed. Okay, so it looks like we're doing some classes here. 28 students took PE, 31 took a biology class, 42 took an English class, 9 took a PE and a biology class, 10 took biology and English, and 4 took all 3. Okay, so we're going to do a Venn diagram of the students who took PE, the students who took biology, and the students who took English. And by this very last bullet, we know that there are going to be some people that took all 3. So we're going to have a Venn diagram that has some overlapping circles. Now let me first actually start by writing PE is one circle. Another circle is going to be the biology. And then another circle is going to be the English. And when we have 3 that interact with each other, we have a potential relationship that looks something like this. Now, there were 100 people in this survey. Let me shrink that down slightly. So we're working with a universe of 100 students, right? So maybe some students didn't take any of these classes. That's something that we don't necessarily have a statement that says that, but that might be the case if there's some people unaccounted for. Let's see what happens. Let's start with the bottom bullet. This is going to be the most useful information, I think. 4 people took all 3 subjects. So I know definitely there's going to be a total of 4 people there. And that 4 is not the element 4. It's standing for 4 elements are in that, right? So there would be, 4 people. Each person's a dot would be in that intersection of all 3. But let's go ahead and just do counts of how many dots would be in each of these sections by putting a 4 here, right? This is a little bit different than what we did up here, where the numbers represented elements themselves. Now the number here represents how many elements are in this portion. Okay, 28 people took PE. So when looking at PE, there's 28 total people in the PE circle. So I don't know how many to put in these portions. I just know that the total of the 3 question marks and the 4 have to be 28. So I'm not sure how useful that 28 figure is right now. Let's just kind of work with our data from bottom up and see what happens. 10 people took biology and English. Okay, well, the biology and English overlap is right here. There should be 10 people in this portion. And if I know that 4 of them also took PE, then I know how many did not take PE, and that has to be 6. Right, so I get to fill in this information. So now you can see, the 10 people who took English and biology. Be careful when you see this data that you don't assume that this is trying to say 10 people took English and biology but did not take PE. That's not at all what this is saying. It's just saying 10 people took biology and English, and it turns out that 4 of those 10 people also took PE. Okay, 9 people took PE and biology. So now we're focused on the PE biology overlap, which is right here. 9 people took PE and biology. Well, 4 of them also took English, so that leaves 5 who did not take English. So there's going to be 5 in that portion, so that the total of this intersection is 9. Let's see. Again, working up. 42 people took English. Okay. 9 people took biology. 42 people took English. 31 people took biology. I'm hesitant to work with this English because there's a question mark and a question mark. I know that all of this should add to 42, but I have 2 question marks there right now. So let's skip that data point and see if we're going to be able to resolve this given the data that we have. Let's go up to this 31 people took biology. Well, if 31 people took biology, and the biology circle is all this, then how many people have we already accounted for in those other portions? Well, we have 15 over there, and 31 total took biology. So that means that subtract 15 from 31, and we get 16. There must have been 16 people in the biology, but not the others circle, portion of the biology circle. Uh, 28 people took PE, and 42 people took English. All right. Oops. I don't know why that keeps happening. I don't want you to be there. Go away. Thank you. Do we have enough information here to finish this task? Let's see what we can do with this. Okay, I know that there's going to be some number here, and some number here, and some number here. And we know that B plus A plus, so I'm just counting everything that's in the PE column, plus 9, and we know that has to be 28, because 28 people took PE. We also now, and I'm going to look at all the English stuff, we know that C plus A plus 10 has to be how many people took English, which is 42. Okay, let's see what's going on here with this. Let's do some subtraction, get those constants to the other side. So I know that B plus A should be 19, and C plus A should be 32. Okay, where is this? Where are we going with this? Is this even going to be, do we have enough information here to finish this problem? And we had a total of 100 students interviewed. I'm thinking that we maybe need more information. That's my first impression here, that we need more information. Let's say that nobody, let's just for the sake of argument, just so that we have multiple answers, let's say that nobody took PE and English but did not take biology. If that were the case, and we knew that, so that would essentially mean that these A's were 0. So we would know that the number of people who took PE but not English or biology had to be 19. So that we have 28 total people here in that circle. And then this portion of the English circle would have to be 32, so that the total English is 42. And let's see what our count is at currently. Remember, there's 100 students, and do we arrive at any sort of contradiction here? So we're going to start just counting all these little pieces up. So there's 42 right here. That's going to be 58 plus 5 more, 63 plus 19 more will be 82, which means that there's going to be 18 students unaccounted for that would have to be out there. Now, for the sake of argument, let's say that there happened to be one person that took both English and PE. Well, that's going to have to knock this number down. Oh, I don't know what happened to that one. There's the one. That 19 is going to have to be knocked down to 18. And this 32 is going to have to be knocked down to 31. And as a consequence of this, we're going to have to get one number higher here to get 19, so that everything adds up to 100. So it looks like we are getting, multiple answers depending on how many people took English and biology. This might be a typo on my part, so let's, for the sake of being able to get a unique answer, let's do the following. Let's say that 12 people took PE and English. So just go ahead and make this extra bullet in there on our notes, and then let's see what we can do to finish this problem. All right, so if 12 took PE and English, so now we're looking at this overlap, and 4 of them also took biology, then that leaves a total of 8 people in this portion of the Venn diagram. Now we're in a position, right, where we can put conclusive numbers in the rest of this. All right, so let's focus on the English part right here. 42 took English, and there's 18 right here already. So that takes us down to, 24 left, unaccounted for. Right, but 24 plus 10 is 34, plus 8 would be 42. And 28 people took PE, and we already have 17 accounted for right there. That leaves 11 unaccounted for to put in the PE circle. Now let's go ahead and do all of our adding and see what we get. So we have a total of 42 people in the English, plus this 16 makes 58, plus this 5 makes 63, plus this 11, that's 58, 63 makes 74, which means we have 26 people unaccounted for out of the 100 who were surveyed. Okay, I hope all of my mental arithmetic is correct and that this does in fact add to 100 people. And let's see what we can now do about answering these questions. A, how many took none of the 3 subjects? Well, that would be the 26. How many students took PE but not bio or English? Well, that's going to be this 11 figure. How many students took biology and PE but not English? So now we're looking at the biology and PE overlap, but we have to now say but not English. So that's just going to be this portion right here. So that's going to be 5. And yeah, that's it. That's the end of the real challenge of this one was just creating that Venn diagram and getting the right numbers in the right spots. And then answering some specific questions from that Venn diagram. Okay, that's it for this week's lecture on set theory. Have fun with the homework, and don't forget also some of those interactive activities that you can find on Canvas. Follow those links and do some fun things with sets to test your understanding of all of this theory.